So on page 75, it says we seek to find the average number of left-handed students in any given class.
Oh, neat.
All right. We sample 40 different classrooms. How is sampling variability apply here? All right, well, so, one, did it say anything about random? Red flag right there, okay? 40 different classrooms. Well, it's one thing if, let's say we're at a really tiny school and we only have 40 classrooms total. That might mean something. So this could be, because we want to have a sample size of 30, and we want that to be random. That's basically what we're looking at, but here's the problem. So if we're just looking for, like at Cherry Creek High School, and we wanted to know the percent of left-handed people, let's say we knew that, I don't know, let's just make this up. Let's say that 15% of U.S. people are left-handed. I don't know if this is true or not. Let's say we have a standard deviation of 1.2%. Again, I don't know if this is true or not. I'm just making this up. It's already bummed out on me. I wrote one thing. All right, so being that we don't, if we're just curious of Cherry Creek High School, that's one thing. If we don't know anything else, or we're not looking for anything else, that's different. But we could probably find the national average and the standard deviation of the national average, and that would be fine. But there is variability because, let's say I picked 40 classrooms to use. And let's say I randomly chose 40 classrooms. Now, I would imagine it would be safe to say that our school has more than 40 classrooms. Right? What did I do? So is it possible that if I select 40 classrooms, oh my gosh, this is getting so goofy on me. If I were to select 40 classrooms here at Cherry Creek, which we have more than 40 classrooms easily, and then I selected 40 more random classrooms here at Cherry Creek, let's just pretend they said that we were randomly selecting. It is possible that we would get a different number of left-handed people per every 40 classrooms that we got to. Okay? Hey, James, can you do me a favor? You see that light can you push that back up? I think it has to snap into place somehow. Kinda. Oh.
Don't let it fall on you, James.
It's not? Push it like from the middle as well. Huh. All right. Do me a favor. Just yank that plastic thing down. Yeah, just don't pull the whole light fixture. I just pulled it. And bring it up to me, just so it doesn't fall on somebody. Trying to save lawsuits that might take place. Maybe you guys want to be a part of it. I don't know. Thanks, James. All right. So that's how you answer number one. Number two says a student wants to select 40 different classrooms throughout Creek and count the number of left-handed students in each one. The student chooses classrooms arbitrarily as he wanders the West Building on campus. Why is this not a random selection? Well, it says right there that he goes to just the West Building to check. So it might be, but possible, but not likely, that there might be students that might not have any classes in the West Building. I don't know. So that wouldn't fall into what very well. Yeah.
How does sampling variability apply?
So the hard thing is we don't have random, but let's pretend they did say it's randomly selected. So if I were to select 40 random classrooms and then select another 40 random classrooms and just keep repeating it, because we have more than 40 classrooms here on campus, right? So if I keep selecting 40 classrooms, it's possible that, you know, the more and more you keep selecting randomly, the closer and closer you would get to what the actual mean of the United States would be. But, you know, like Ryan said he's left-handed. Is anyone else in this class left-handed? We got 2 people. So we got 2 out of 30 people.
So it's just like not enough.
Yeah. Hey, good to see you. We're on page 75. So, yeah, I mean, you have enough, because you're selecting 40 classes. I mean, if each class is roughly this size, that's a lot of people. So that it's not going to change too much as far as your population numbers go. But if you didn't make it random, that's a big, you know, marker there that says, hey, this is bad. Holy cow, what's going on here? All right, so hopefully I can get through this without talking much more. All right, did I answer your question? You feel good about that? Okay. So a lot of times on these kind of questions, like, use your common sense to say, well, I don't know, like if I went down the hallway and around the corner and just picked.
How about you just tell me what sampling variability even means?
Oh, so let's say we happen to know the national average. Okay. If I sample a certain selection of people, it's possible I could find 40 classrooms that nobody's left-handed in. So then you would have a 0. And then if you go to another 40, it's possible you might find a couple classes that might have like 30%. And so like it kind of, what the variability means this. I know this is the mean. Let's pretend we know this is the mean right here, my arm. Okay? Some number that we just happen to know. But let's say as we go through, we get numbers to the left, we get a mean to the left, we get a mean to the right of our samples. And what basically happens is the more and more samples you do, they start regressing back to what the mean is eventually. So, you know, you have plenty of people you're sampling, but it won't always hit the mean. And there's always a chance that we're... There we go. All right. All right. Number 3. Number 3. Traditionally, ACT scores normally distributed with a population mean of 18. So they're telling us we're getting this mean of 18. And population standard deviation of 6. So what, excuse me. So this is number 3. So for 3A, what would the mean be of the sample? The mean is going to be 18. And then my standard error, which is the same thing as standard deviation, but it's your standard deviation of a sample, becomes this over the square root of n. So I'm going to go 18 divided by the square root of, if you had a sample size of 100. So this would come out to be 1.8. So my standard error of my sample becomes 1.8. So what you kind of have to think about with this is if you did, this was your national average normal curve, whereas all of a sudden this blue, which I shouldn't have shown as in blue and black, but this blue right here becomes our sample standard error. So the standard error is very similar to the standard deviation. In fact, a lot of times they will say the standard error is the standard deviation of your sample that you selected. In this case, it was 100 people. Okay, so if we wanted to create a normal distribution based on this, we wanted to do the standard, so if this was our sample and we were to make a normal curve, we would know that the 18 is here, but we know that the standard error was, well, hello. You're going, yeah, I heard. All right, so what I want to do is I want to create my 7 positions based using the 1.8, not my 7 positions based on my standard deviation. All right, so I'm going to use 1.8 rather than going out 6. So if I go 1.8 this way, this is going to become 19.8. If I add 1.8 to that, 6, carry the 1, 10, 21.6. And then this add 8 to 1.8 to this, that's 4. Carry the 1, that's 3. Put the decimal there. So 23.4. If I go this way, if I go 18 minus 1.8, 17.2. 17.2. And then subtract 1.8 from that to get here. 15.6. Let's see, that's going to be a 15.4. And then subtract 1.8. My math might be wrong. I'm not perfect. You know that. 6. Okay, so that's your normal distribution with the 7 positions based on your sample where you're using your standard error, not using the standard deviation. Okay? And then what percent of all random scores, sample size 100, possesses an average ACT score greater than 20? All right, so is it 0.2? I don't know. Here, let's do this. Let's just jump it to Desmos. On what? So normal distribution based on 18. What percent of random sample size 100 presents? Okay, so then I have to put my standard error in. What I said, standard error I said was 1.8. So if we wanted to look at 20 or higher based on this, so now you're talking about 13%. But if I did my normal distribution, so that's using my standard error. But if I did my normal distribution based on the national average, 18,6, and I did this as being 20. So look at how it changes. So my national average and the normal curve should look different, and that's fine. But if I base this off my national average using my standard deviation of 6, and we wanted to select one person randomly out of that group of people, what's the probability they have a score of 20 or higher? You have almost a 37% chance. But if you were doing your sample of the 100, if you keep taking a sample of 100, keep doing a sample of 100, basically the probability that somebody gets above a 20 is yielding down to a 13.3% chance. Okay, so you're getting a much lesser percent chance because of that. Was it 1.8 or was it 0.18? I don't remember. 1.8. Okay, we're right. All right. And assume a basketball player is scoring that is normally distributed with a population mean of 24 points per game and population standard deviation of 4. Okay, so we can do this. So let's make this based on, we'll just do this as the normal distribution, 24, 4, and I'm not worried about this. And then, so create a normal distribution with all 7 positions. Okay, so a normal distribution based on this in all 4 positions. Okay, you would go 24, 28, 32, 36, 20, 16, 12 would be your markers on this. That'd be your 7 positions. And then what percentage of all of his games will result him scoring 29 or more points? Okay, so if I wanted to do 29 or more points, I'm going to go 29 here. And so there's roughly a 10.6% chance of happening. Okay. Yeah, so that was just normal distribution that we're used to. And then create a normal curve if the person had 81 games. All right. All right, so we're going to go 4 divided by square root 81. And that becomes that. And if we wanted to know, so take a look at this. Shh. Oops, that's supposed to be 24 here. I'm sorry. All right, so the blue is that based on the 81 games having the standard error in place, going 4 divided by square root 81. Then, so what percentage of all season group? Okay, so create the normal distribution of this of 8 games. So I don't know what 4 over 9 is. 4 divided by 9. So it's 0.4. So on this particular one, we'd go 24, 24.4, 24.8, 25.2, and then subtracting, you'd get 23.6, 23.2, and 22.8. That's based on that. And this is what percentage of all the seasons, groups, 81 games, will result in 30 or more points. Ooh, 30 or more points. Oh my gosh. So what they're doing in this case is they're saying, okay, we know we have this person who scores 24 points with a standard deviation of 4 normally. But then we have the standard error because we have 41, we have our 81 games total. So our standard error is 0.4 rather than using our standard deviation. And the probability that this person scored 30 or more points in every game in all 81 games, you're talking about 7.8 times 10 to the negative 42 power. So this event here, the probability that they normally had 24 and 4, and we're now basing it on 81 games. So the probability in all 81 games that they score 30 or more is so very unlikely. I mean, it's already pretty unlikely, and we did 29 here and got a 10% chance for a one-time thing of randomly selecting the game. But if I randomly selected all 30 games and took a look at it, they have a really low probability of it taking place. So the standard error during why you use it is, do we really have a chance of this happening? I mean, yeah, I say there is a chance, but you have a better chance of getting struck by lightning 14 times on your way to go buy a winning lottery ticket. Okay? I mean, it's not as likely to happen. And then number 5 says a psychological evaluation is performed on memory retention. Memory retention scores are normally distributed with a mean of 200 and standard deviation of 400 or 40, excuse me. So if we do a normal distribution on that, you'd have 200 in the middle, go 240, 280, 320. The other way, you'd go 200 in the middle, 160, 120, 180. Or wait, I went backwards. If you went 20 or 200 in the middle, it goes to 160, 120, and then 80 for your normal distribution. I'm pretty sure you're okay. Calculate the probability of individual memory retention. He will score between 150 and 250. All right, so let me take away this one. Let's do our normal distribution up here. And we're going to just do this based on this is last semester stuff, 200, comma, 40, what's the probability this person scores between 150 and 250? So I'll make that 150. I'm going to make that 250. So looking at the top, we have like almost a 79% chance of that person's going to score within that region. So that's more than one standard deviation. Okay. So then we're going to change that to, how is this going to change? So I'm going to still stay with the mean being 200. And then I'm going to do my sampling variability, which is going to be 40 divided by the square root of 25. So this basically becomes 4 divided by 5, which is 0.8, or 40 divided by 5, excuse me, I made a mistake. 40 divided by 5. So it goes from a standard deviation of 40 to a standard error of 8. And so if you create a normal distribution based on this, you'd go 200, 208, 216, 224, 200 in the middle, 192, 184, 176. That's your 7 positions. And then calculate the probability that this person scores between 150 and 250. So 150 and 250. I'll turn that one on. So take a look at this. Be good.
I'll see you later. I'll see
Yeah.
you tomorrow.
Yes. So the big difference between the two is you have 25 events taking place here, so you create the standard error being 8. But look at what happens. If you just did the normal distribution between 20 and 40, and you said, what's the likelihood that you select one of these people that they score between 150 and 250 is like 78.9%. But if I said in all 25 events, my standard error my standard deviation goes from 40 to 40 over root 25, which is 8. So 200, 8. So the chance to score between 150 and 250 is very close to 1. It's 0.9 repeating until you get to like 9 spots over and you have a 5. Okay, so this is a very likely event of taking place. As the sample size rises, explains what happens to the standard error. Okay. So as the sample increases, what happens to the standard error? Well, the standard error equation is this. Okay. So if our sample gets larger, bigger and bigger and bigger, this becomes smaller. So as your sample size gets bigger, the sample standard error gets smaller. Okay? And then the mean of the sampling distribution. The mean will stay the same. The mean is the same. Okay, it's not going to change. The probability that the average or a random sample will be between 150 and 250. Okay, so as our standard error, as our sample gets bigger and bigger and bigger, our standard error gets smaller and smaller and smaller, which means I'm going to capture more and more and more in this scenario between the 150 and 250. Okay, it doesn't always happen that way. But as far as if I'm going between two different values, those two different values based on a normal distribution, just a singleton where you use the standard deviation, is going to be a certain percent that's going to fall between that. But as this gets bigger and bigger and bigger, this denominator gets bigger and bigger and bigger, that becomes smaller and smaller and smaller. So we don't have to necessarily think that it's going to become 0. In fact, when I have this in place and I'm going between two things that are above and below, like I just did. So when you look at the 150 and 250 in this scenario, well, the 150 is 50 below, the 250 is 50 above. So we're still doing the same thing here, but because this is going to shrink the standard error, and when it shrinks the standard error, because we're between the same regions, this gets so close to 1, this is 78.9%. So that is what we got. Okay, now questions about that. I know I just kind of covered a whole plethora of information. What do you think? Okay, does it logically make sense why in this case we approach 1 with a standard error, whereas the other ones, if I went back to the other ones where I was talking about what's the chance, so there's 2 different things that I want you to think about. Okay, if I were looking for like this, or if I were looking something like this, okay, our standard error, which is the standard deviation over the square root of the sample size, this becomes less likely in this scenario. Okay? For these 2 scenarios, this type of thing where you're looking to the right or to the left, that's going to become less likely to happen. But if I said, hey, I wanted to know a region in between like this, and I use my standard error, again, which is this, as n gets bigger, this becomes more likely. So this is more likely to happen. Okay, and I gotta go here. So this case becomes more likely. Okay, so again, so kind of think to yourself, maybe make a little note off something. If I'm looking for an end or an end, and I create a sample, if my n gets bigger, this becomes less likely to take place, because this is saying that what's the chance that all of these n events would take place in this little tiny region here or this little tiny region here. If you're dealing with in between 2 things, and your n becomes larger and larger, this becomes more likely that all of your events will fall between those 2 bound regions. So a bound region becomes more likely. An unbound, meaning I go from a number to infinity or a number to negative infinity, that becomes less likely to take place the more samples you take. Okay? Make sense? Hey friends, I was planning on just being able to teach 5-4 tomorrow. Is that okay? That means you don't have any homework tonight?
It's okay, Mr. Sir.